We need to adjust the stress points here. The timber won't hold otherwise.
All right, I'll update the schematics now.
We have to rework the plating schematic. The tolerances are too loose.
If we don't fix this now, the shipyard will reject the whole run.
Check the tolerances on these rivets again, soldier.
Yes, sir. They seem secure, but I'll double-check the specifications.
January 17th, 1940. The cold Pennsylvania dawn presses against the steel-clad walls of Bethlehem Steel. Smokestacks pierce the gray sky, belching black clouds into the frigid morning. The air is thick with the smell of molten metal and coal, a biting mixture that stings the lungs of the men who toil in the furnaces below. Sparks fly from red-hot ingots as they are hammered and rolled, echoing like distant gunfire across the cavernous mills. Outside, trucks loaded with timbers and equipment rattle along frost-covered roads, waiting for steel that simply does not exist. The military's demand for bridges grows urgent. Armor divisions cannot move, supply lines cannot stretch, and the world teeters on the edge of war. Engineers in soot-streaked overalls hunch over blueprints, pencils scratching revisions for a steel that is thinner, lighter, yet somehow stronger. Every molten pore, every rivet hammered, carries the weight of the nation's readiness. The men working in the shadows of towering cranes know their labor is not just industry. It is preparation for a conflict that may engulf the world. In these moments, the impossible becomes a challenge, and ingenuity is forged alongside iron and alloy. The question is not whether Bethlehem can supply bridges, but how. The scene now shifts from a mill and its smoke-choked skies to the pressures shaping America's steel crisis in 1940. By 1940, the world had already been at war for over 18 months. Europe was burning. Poland had fallen, France teetered under German occupation, and the Luftwaffe rained terror across the skies. Across the Atlantic, the United States remained officially neutral, but neutrality did not spare it from preparation. The military expansion was urgent, driven by the realization that America's industrial might would soon decide whether it could project power overseas or be crushed if war reached its shores. Steel was the backbone of this preparation. It was the skeleton of ships, the arteries of tanks, and the bridges over rivers that allowed armies to move with speed and coordination. Yet in 1940, American steel production, though vast, was already under strain. Civilian industries still dominated the output. Automobiles, rail cars, and construction projects consumed much of the available metal. Military demands, particularly for bridges strong enough to support heavy vehicles, were increasing faster than the mills could supply. Bethlehem Steel, Pennsylvania's industrial giant, stood at the heart of the nation's response. Its furnaces, some nearly a century old, were working at full capacity. Outside, railroad yards hummed as flat cars delivered raw ore, and smokestacks cast long shadows across frostbitten yards. Inside, engineers scrutinized designs with a growing concern. The alloys available were not sufficient for the Army's requirements. Bridges had to support tanks weighing upwards of 30 tons. Yet the high-grade steel normally used in such constructions was being rationed for naval vessels and shipbuilding contracts. The shortage was not merely numerical, it was technical. Traditional bridge steel could not be stretched thinner or forged faster without losing strength. Every mile of highway, every river crossing, became a logistical puzzle. Military planners calculated the number of bridges needed for possible scenarios. armored divisions crossing the plains, infantry advancing through river valleys, supply convoys moving hundreds of miles inland. The numbers were stark. The Army estimated that, to fully prepare the eastern and midwestern defensive networks, it would need more than 150,000 tons of bridge-grade steel. Yet the available inventory fell far short. Into this vacuum stepped Bethlehem engineers and metallurgists. Led by veterans of the steel industry and wartime contracts, they began experimenting with alloys, mixing manganese, nickel, and chromium in precise ratios to produce steel that was lighter but retained remarkable tensile strength. The techniques were delicate. Temperatures had to be exact, rolling speeds controlled, and cooling carefully monitored. Too fast, and the steel would crack under stress. Too slow, and production fell behind schedule. Every day was a race against the calendar, against the military's needs, and against the realities of physics. Meanwhile, across the country, government officials applied pressure. The War Department sent emissaries to mills demanding progress reports. Engineers traveled to Washington to justify technical decisions, armed with charts, stress tests, and samples of new alloys. Decisions that might take months in peacetime were compressed into weeks, then days. Political leaders understood that bridges were not abstract. They were the literal paths over which men and machines would march in the event of a European or Pacific conflict spilling onto American soil. The pressure extended beyond the mills. Labor disputes, strikes, and wage negotiations could halt production at a moment's notice. Bethlehem's managers walked a fine line, balancing the demands of workers with the imperatives of national defense. Night shifts extended into early mornings, and the smell of molten metal became a constant companion to the engineers and foremen. Amid this, innovation flourished. Techniques that had previously been theoretical, such as the controlled addition of rare alloys to increase ductility, were suddenly tested on massive beams destined for construction. Logistics compounded the challenge. The steel was produced in Bethlehem, but the bridges had to be assembled across rivers, in locations that were often remote or difficult to access. Flat cars, trucks, and cranes were allocated with military precision. Engineers calculated every bolt, every girder, every rivet. Failures could mean delays measured in weeks, or bridges unable to carry the necessary loads. For soldiers and planners alike, a bridge was not just infrastructure, it was a lifeline. The crisis revealed another dimension of industrial warfare, the interdependence of civilian and military priorities. While Bethlehem focused on alloy innovations, other steel producers were diverted to ship hulls, ammunition, and aircraft engines. The shortages forced engineers to be not just metallurgists, but inventors, tacticians, and logisticians. They experimented with hybrid designs, steel reinforced with concrete cores, beams layered to distribute weight, joints re-engineered to withstand dynamic loads. Every test brought new insights, but also new anxieties. Would the Army approve the novel methods? Could the bridges hold in winter or under the weight of mechanized divisions? By late 1940, some solutions had begun to emerge. Alloy reinforcements allowed beams to be thinner yet stronger. Prefabrication techniques reduced assembly times in the field. Engineers documented every step, aware that these innovations could define the speed and mobility of American forces in a coming war. Yet even as progress was made, the shadow of urgency never lifted. Europe's battles continued unabated. German panzers rolled across France, and in Britain, steel rationing mirrored America's struggles. The industrial race was global, and failure at home could have consequences on a battlefield thousands of miles away. The stakes were not abstract numbers on a ledger. They were human. Soldiers training on riversides in upstate New York or the Midwest relied on bridges that did not yet exist. Generals planned maneuvers assuming crossings that might fail if steel quality faltered. And Bethlehem's workers, sweating over furnaces and blueprints, understood that their labor carried a silent but immense responsibility to transform shortage into strength, to convert scarcity into steel that could save lives. Every calculation, every alloy mixture, every beam cast and rolled was a step toward bridging the gap, not just across rivers, but across a nation on the verge of global war. From the furnaces of Bethlehem to the far reaches of America's defensive lines, innovation and necessity collided. It was here, amid smoke, sparks, and the clang of iron, that the story of America's wartime steel ingenuity began. And as the first experimental beams left Bethlehem, destined for riverside test sites, the engineers knew that these small triumphs would soon face their ultimate trial in the field, a trial that would determine whether American ingenuity could overcome the limits of raw materials and whether the nation could meet the coming storm of war. Inside Bethlehem Steel, the furnaces roared like a living thing. Engineers huddled over blueprints, their faces streaked with soot and sweat, pencils sketching last-minute adjustments. The men were exhausted, yet their focus never wavered. They were tasked with a challenge that blurred the line between engineering and improvisation, creating steel that could bear the weight of tanks, trucks, and artillery, while compensating for the nation's shortage of raw material. One metallurgist adjusted the ratio of manganese and nickel in a steel sample. The furnace temperature was critical, a few degrees too high, and the alloy would lose its tensile strength, becoming brittle under load. A slight miscalculation, and a bridge could collapse under the first convoy. Workers coordinated in near silence, communicating through hand signals above the din of rolling mills and hammering presses. Each molten pour felt like a gamble with fate. The human cost was visible. Burns, exhaustion, and the constant pressure of looming deadlines marked every day. Yet there was pride as well. The men knew their work would directly impact soldiers preparing for war. Each rivet hammered and each beam rolled was a small act of national defense. Bethlehem Steel's human machinery, hands, minds, and sweat, was as essential as the furnaces themselves. The Army's need for bridges was immediate and unforgiving. Planners envisioned armored columns moving at speed across rivers in New England, the Midwest, and strategic points along the eastern seaboard. Delays were unacceptable. Without bridges, units would be stalled, supply lines interrupted, and defensive positions compromised. Military officers worked closely with Bethlehem engineers, providing specifications down to the smallest detail, load capacities, span lengths, and deployment timeframes. Tactical considerations were exacting. Bridges could not simply support static loads. They had to endure dynamic stress from moving tanks, artillery, and trucks. Engineers developed modular designs, enabling quicker assembly in the field. Test sections were transported to nearby rivers, where Army engineers subjected them to repeated stress tests. Vehicles rolling back and forth for hours, beams bending under weight, but holding firm. The stakes were higher than a classroom experiment. Each failure meant redesign, lost time, and risk to soldiers' lives. Traditional steel was insufficient. Bethlehem's solution was a subtle marriage of metallurgy and innovation. By introducing higher percentages of manganese, carefully controlling carbon content, and tempering with precise heat cycles, engineers produced steel that was both lighter and stronger. Rolling techniques were adapted. Beams were layered and compressed, creating internal structures that resisted bending and torsion. Cranes lifted glowing beams onto test racks, and engineers observed minute deflections under load. They documented everything: temperature fluctuations, alloy ratios, and stress responses. This was industrial research at scale, conducted under pressure in real time. The work would influence future military engineering and set a precedent for alloy-based structural solutions. Bethlehem's leadership had to balance multiple pressures simultaneously. Plant managers coordinated with Washington officials, negotiating delivery timelines while ensuring workers were safe and production remained consistent. War Department inspectors arrived without warning, reviewing processes and demanding updates on experimental alloys. Leadership decisions had to be rapid, precise, and backed by technical understanding. Orders from above were uncompromising. "The Army needs bridges now," read one cable. Bethlehem's executives understood that delays were unacceptable. Yet within the plant, leaders had to maintain morale and efficiency. Night shifts were scheduled, engineers rotated, and safety measures enforced. Small decisions with significant consequences. The bridge between industrial labor and military necessity was as much about people as it was about steel. Across the ocean, German military planners watched America's industrial output with interest. Though the U.S. was neutral in 1940, intelligence reports noted the growth of production capabilities. If the United States could rapidly deploy mobile bridges, it would allow troops to maneuver efficiently, reinforcing coastal defenses and potentially supporting Allied operations abroad. The shortage of steel, while acute, also highlighted the strategic advantage of innovation. Whereas Germany relied on existing steel reserves and standard designs, America's experiments with alloys and modular bridge construction hinted at a flexibility that could surprise an adversary. Each reinforced beam tested in Pennsylvania represented a potential advantage thousands of miles away, a silent contributor to strategic deterrence. The steel shortage forced hard decisions. Civilian projects were delayed, construction contracts postponed, and certain industries faced rationing. Bethlehem and the War Department had to prioritize military needs over commercial profits. Workers and engineers were caught in the tension between national duty and economic livelihood. The moral weight was palpable. These men were producing infrastructure that could save lives in the field, yet every delay in production could have ripple effects across communities and industries. Ethical considerations blended with pragmatism. The question was not whether to innovate, but how fast innovation could be safely applied without compromising the workforce or the end product. Bethlehem Steel became a symbol of America's industrial resolve. The plant's towering furnaces, glowing red against the winter sky, were a testament to human ingenuity under pressure. Workers, engineers, and leaders alike shared a sense of purpose to transform shortage into strength. Newspapers chronicled milestones, praising the workforce, while families followed updates with quiet pride. This shared effort mirrored broader societal mobilization. Factories across the nation experimented with similar innovations, from aluminum alloys for aircraft to modular ship components. Bethlehem's bridges were one visible, tangible piece of a much larger mosaic, a nation preparing for war with intellect, labor, and ingenuity. By the end of 1940, the fusion of engineering, alloy innovation, and military requirements began to yield practical solutions. Experimental beams were deployed to test sites, trucks rolled across steel under carefully measured weights, and engineers recorded results with meticulous precision. The process was iterative. Failures occurred, adjustments were made, and knowledge accumulated. Each successful test brought not just a stronger beam, but a deeper understanding of how technology and strategy could merge under industrial constraints. Through these angles, human, tactical, technological, leadership, enemy, moral, and social, the steel shortage crisis became more than a logistical problem. It was a story of resilience, ingenuity, and foresight. The stakes were both immediate and symbolic. Whether the United States could convert scarcity into strength, and whether its industrial heart could support a nation on the brink of global conflict. The stage was now set for the ultimate test. The bridges would leave the mill and meet the real world. Deployment, field trials, and adaptation would mark the turning point in America's response to the steel crisis, a climax that would determine if alloy ingenuity could truly carry the weight of war. Spring 1941. The air along the Delaware River was thick with mist and the scent of wet earth. Flat cars rolled up to temporary assembly sites, carrying the first experimental beams forged in Bethlehem. Soldiers stood at attention, their boots sinking slightly into mud, eyes fixed on the steel that might determine the mobility of America's armored divisions. Engineers followed, clipboards in hand, pencils poised, each aware that every calculation, every rivet, and every weld was about to face its ultimate test. The first bridge was a modest span, only a few dozen feet, but its weight capacity had been rigorously calculated. Tanks, weighing over 30 tons, would roll across it. As the first Sherman tank rolled onto the beams, engineers watched strain gauges, primitive by modern standards, but critical tools, recording the stresses. The steel shivered, flexed, and held. A collective exhale rippled through the assembly team. For a moment, it seemed that innovation had triumphed over scarcity. But the moment of triumph was fleeting. The next test brought multiple vehicles in tandem, simulating the stress of an armored column crossing in rapid succession. One beam creaked alarmingly, a high-pitched groan that silenced the field. Engineers ran calculations on the spot, revising support angles, reinforcing joints with temporary shims, and reapplying tension bolts. Failure, they realized, was not a distant possibility. It was inevitable until refinement matched ingenuity. Night fell, and the bridge site was illuminated by floodlights. Sparks flew from welding torches as engineers worked in shifts, correcting flaws discovered during the day. Soldiers helped roll supports into position, the hum of engines echoing against the riverbanks. For hours, Bethlehem's alloys were subjected to repeated stress. Tanks reversing, artillery rolling, trucks loaded with concrete crossing and recrossing. Every successful traversal was logged, every fracture analyzed. In parallel, larger bridges were assembled farther upstream, where wider rivers required spans that had never been attempted with the new alloy techniques. Here, failure struck more dramatically. A mid-span beam bent excessively under a convoy, forcing engineers to jerry-rig temporary reinforcements. Reports were sent back to Bethlehem Steel headquarters, data, diagrams, and photographic evidence. Engineers back at the mill stayed up nights, recalculating alloy compositions and rolling schedules, knowing that the next batch of steel would need to perform flawlessly. Leadership at the War Department grew anxious. Cables arrived, demanding progress updates. Time is critical, one message read. The 1st Armored Divisions are scheduled for maneuvers. Bridges must support movement without delay. Bethlehem executives convened emergency sessions, reviewing results with metallurgists and military engineers. Solutions were debated: thicker beams, modified tempering, or layered supports. Every adjustment needed rapid implementation, as delays could cascade into national readiness gaps. By midsummer 1941, progress began to solidify. Iterative testing had refined beam compositions and structural designs. Engineers discovered that layering steel with complementary alloys in a precise sequence distributed stress more evenly, while reinforced joints prevented torsion-related failures. Modular designs allowed beams to be assembled in sections, reducing the risk of catastrophic collapse and speeding deployment. Bridges were now crossing rivers successfully under full military loads, tested repeatedly under both static and dynamic conditions. Field trials extended beyond the Delaware. Sites in upstate New York, Ohio, and the Midwest tested beams under freezing winter conditions, heavy rainfall, and high winds. Each environment introduced new variables. Steel contracted in cold, moisture-threatened rivets, and uneven riverbeds challenged stability. Engineers adapted, introducing small but crucial innovations: additional cross-bracing, corrosion-resistant coatings, and reinforced anchoring points. Each success was hard-won, the result of hundreds of hands, dozens of minds, and countless hours of trial and error. One particularly tense sequence occurred during a demonstration for high-ranking Army officers. A convoy of fully loaded trucks, artillery pieces, and armored vehicles crossed a river at a speed simulating combat movement. One beam bent perceptibly under the weight, and a hushed murmur rippled through the observers. Engineers quickly assessed the structure, confirming that the deflection was within safe limits. The convoy crossed safely, a moment that earned quiet nods of approval. This was the moment when innovation proved its worth, not in theory, but in practice. The climax reached its peak with the deployment of a bridge over the Allegheny River, designed to support multiple armored divisions in a simulated wartime scenario. Dozens of trucks and tanks rolled across, each crossing pushing the limits of the new alloy-reinforced beams. Observers counted microfractures, noted beam deflections, and compared them to predictions. When a last vehicle passed and the steel held without failure, the engineers allowed themselves a rare moment of celebration. The impossible, building bridges capable of supporting a modern mechanized army under steel shortages, had been achieved. This turning point was not just about material success. It was about confidence. Military planners could now trust that bridges, once considered a vulnerability, would not impede troop movements. Engineers had transformed scarcity into strength, applying both science and practical experience. The Army could plan maneuvers with assurance, soldiers could train without fear of infrastructure collapse, and Bethlehem Steel had proven its ability to innovate under immense pressure. Yet even in victory, caution prevailed. Engineers knew that field conditions could still challenge the designs. Every bridge built would need monitoring, every convoy crossing measured for stress. War was approaching, and these structures would soon be tested under real combat conditions. The triumph of alloy and ingenuity was only the beginning. A bridge not just across rivers, but into America's readiness for the global conflict that was inevitable. The successful deployment of these bridges naturally led to the next chapter. Aftermath, where the consequences of these innovations, strategic, industrial, and human, would unfold, defining America's approach to wartime production and preparedness. The morning after the final tests, the Delaware River was quiet. Mist rose from the surface, curling around steel beams that now spanned the water with unshakable confidence. Soldiers and engineers walked along the newly completed structures, inspecting joints and rivets, testing handrails, and noting subtle flexes under foot traffic. The successful crossings marked the first tangible victory of America's industrial ingenuity, a moment when human labor, technological innovation, and necessity had converged. Military planners moved swiftly to capitalize on this success. Detailed reports, complete with photographs, stress charts, and metallurgical analyses, were dispatched to War Department headquarters in Washington. Commanders used the data to revise operational plans, factoring in bridge reliability into deployment strategies. Armored divisions could now train across rivers with certainty. Supply convoys could move without the fear of structural failure. The strategic calculus had changed. Across Pennsylvania, Bethlehem Steel's mills were lauded for their achievement, but the work was far from over. Production schedules were expanded, and additional shifts were added to meet the growing demand for bridges across the eastern and midwestern states. Engineers refined rolling techniques, incorporating lessons learned during field trials. Prefabrication methods were standardized, allowing beams to be cut, tempered, and transported in modules, ready for assembly on site. The impact on the workforce was immediate. Engineers gained recognition for problem-solving under pressure, and skilled laborers received bonuses for overtime and extraordinary performance. The mill became a hive of innovation, a place where failure was expected, studied, and corrected with meticulous precision. Workers carried the knowledge that each beam, each rivet, contributed directly to national defense. The human connection between labor and military preparedness had never been more tangible. Industrial consequences extended beyond Bethlehem. Other steel producers began experimenting with similar alloy reinforcements and modular designs, creating a ripple effect across the country. Shipbuilders, railroad companies, and aircraft manufacturers observed and adapted lessons learned from the bridges. America's industrial network had become a living laboratory, demonstrating that scarcity could drive creativity rather than stall production. Economic and political ripples followed as well. The success of alloy-reinforced bridges validated decisions made by the War Department to prioritize military infrastructure over civilian projects. Roads, factories, and civilian construction sometimes faced delays, but the public and political leaders understood the stakes. Newspaper editorials praised the collaboration between engineers, laborers, and the Army, framing it as a testament to American ingenuity and industrial patriotism. The bridges themselves became a silent symbol of preparedness. Armored convoys crossed rivers in exercises, artillery units advanced without hesitation, and logistical planners could calculate troop movements with confidence. Soldiers trained on these bridges knew that the steel beneath their feet was a product of both human perseverance and scientific insight. Each crossing reinforced a sense of security and capability, a reassurance that, should war reach American shores, infrastructure would not be the weak link. Yet the aftermath was not purely celebratory. The pressure of scaling production revealed systemic challenges. Furnaces strained under increased output. Rare alloys had to be sourced carefully, and minor failures during shipping or assembly reminded engineers that perfection was elusive. Emergency protocols were established. Field teams were trained to reinforce beams, replace damaged components, and monitor structural integrity under load. The bridges were strong, but they required vigilance. Strategically, the success of Bethlehem Steel's alloy innovations influenced broader military planning. Armored divisions could now assume rapid river crossings and exercises simulating both domestic defense and overseas deployment. War planners revised mobilization strategies, confident that logistical bottlenecks caused by steel shortages had been mitigated. The bridges enabled not only training, but also the projection of force, a capability that would become crucial in the eventual Allied campaigns across Europe and the Pacific. The human dimension of the aftermath remained profound. Engineers and laborers who had worked through nights and weekends shared a quiet pride, even as new orders arrived. Families visited the mills, observing the glowing furnaces, the rolling beams, and the precise choreography of cranes and riveters. For many, the bridge-building effort became a personal contribution to the nation's defense, a tangible example of how individual skill and collective effort could shape history. By 1942, the lessons from Bethlehem had become institutionalized. Bridge designs were cataloged, alloy recipes recorded, and assembly protocols standardized. Training manuals incorporated insights gained from field trials, ensuring that Army engineers could replicate success anywhere in the country. The combination of metallurgical innovation, military necessity, and industrial discipline had created a model for wartime production, demonstrating how ingenuity could overcome raw material shortages. The bridges also influenced technological thought beyond steel. Engineers recognized that limitations could spark experimentation in other materials: aluminum alloys for aircraft, modular ship components, and reinforced concrete structures for fortifications. Bethlehem Steel's work became a case study in applied industrial problem-solving under pressure, illustrating that scarcity was not an obstacle, but a catalyst for progress. On a larger scale, the successful deployment of alloy-reinforced bridges sent a message internationally. While America remained neutral, intelligence reports and diplomatic observers noted the nation's growing industrial capacity. Potential adversaries understood that the U.S. could not only produce steel, but adapt it creatively to meet military needs. The bridges were more than infrastructure. They were a strategic signal of readiness, resilience, and technical mastery. Yet perhaps the most lasting consequence was cultural. The story of engineers, laborers, and soldiers collaborating under intense pressure became part of the narrative of American ingenuity. Training programs, industrial schools, and wartime propaganda highlighted these bridges as symbols of what coordinated effort, scientific knowledge, and determination could achieve. In communities surrounding Bethlehem, young men and women looked to the mills as a place where skill mattered and where the nation's fate could be shaped by effort and intelligence. As America entered the war following the attack on Pearl Harbor in December 1941, the bridges built and perfected through Bethlehem's alloy innovations became vital. They carried men and machines across rivers, supported supply lines, and enabled strategic mobility in exercises preparing units for deployment overseas. What began as a challenge born of scarcity had become a cornerstone of military preparedness. The aftermath was a fusion of triumph and vigilance. Triumph in overcoming material shortages and proving industrial ingenuity. Vigilance in ensuring that each bridge could withstand the practical realities of war. Engineers, soldiers, and policymakers alike understood that the work of Bethlehem Steel had shifted the balance between limitation and capability. America's industrial heart had beaten under pressure and emerged stronger, ready to support a nation on the brink of global conflict. This sets the stage for the reflection/closure, where the narrative will contemplate the broader significance. Human ingenuity, industrial adaptation, and the quiet, unheralded innovations that shaped the course of history. In the quiet aftermath, when the furnaces cooled and the smoke hung lighter over Bethlehem, the significance of those bridges became clear. They were more than steel and rivets. They were the embodiment of human ingenuity meeting necessity. Scarcity had forced creativity, pressure had forged innovation, and labor had become a form of quiet heroism. Each bridge carried not just vehicles and artillery, but the weight of preparation itself, the knowledge that America could adapt, endure, and overcome. Soldiers who trained upon them might never have known the names of the engineers, metallurgists, or riveters who made their crossings possible. Yet every mile rolled, every tank supported, and every convoy delivered was a testament to the meticulous work done in smoke-filled mills and drafting rooms. Bethlehem Steel's alloy innovations demonstrated a principle that would echo throughout the war. Technology alone was insufficient. It was the combination of intellect, labor, and leadership under pressure that truly determined success. In solving a material shortage, engineers had rewritten the rules of military mobility, showing that ingenuity could compensate for limitations. History often remembers battles and leaders, but the story of steel, its creation, reinforcement, and deployment, remains a quieter narrative of resilience. These bridges connected more than rivers. They connected preparation to possibility, scarcity to strategy, and individual effort to national defense. In the end, the legacy of Bethlehem Steel in 1940-41 is a lesson in human potential under constraint. When the world demands more than resources can provide, determination, innovation, and collaboration can build pathways to survival, and sometimes to triumph. The bridges still stand in memory, silent and unyielding, a reminder that even under pressure, human skill and creativity can span the greatest divides.